Hi, my name is Natarajan. I am a leading data science and ML engineering team for PowerShell Core and Shell. My colleague Raja, he is leading the data engineering team for PowerShell Core and Shell. Today, we will present modern data lakehouse at Shell, and we will walk through one of our projects with the data lakehouse. Yeah. So Raja and I are going to talk about one of the project which we are working for Shell Energy. It's called load forecast. So Shell Energy offer all the electricity need for the customer home. And one of the requirement is to predict long-term and short-term electricity demand. And but the customer electricity usage will vary based on the weather conditions or the social events or holidays, weekdays, weekend. And sometimes weather is unpredictable. And the weather condition is not same for all the customers. So it's very difficult to predict the future load forecast with high accuracy. In this project, we are trying to predict individual customer demand with high accuracy. We will walk through the project details. In this project, we are using classical machine learning algorithm with clustering approach. So initially, we tried to create model based on the load profile, but load profile is static over the time. And actually, it's not given the expected result. So we have created our own cluster using our clustering algorithm. And we have created separate model for each cluster and apply the cluster model for every customers. And we try to monitor and we actually improve the performance of this each cluster. And we deploy all this model in the AWS. And we are running daily forecast with 100+ model. So this is a very high-level architecture. So we hosted everything in the AWS cloud, and we are getting data from multiple data sources. We are getting the usage data from Shell Energy, and we are also getting data from other data sources. And we are getting customer and contract data from Shell Energy. And weather data we are getting from external service provider, and we are getting weather actual and weather forecast data. All this data we are storing in the S3 bucket, and we are accessing through the Dremio. So we are using VDS, reflection, and multi-layer lineage to access the data from Dremio. So we are actually using Dremio to train our model or run the inference. And we are writing the result back to S3 bucket, and our customer is reading the result through the Dremio. In this project, we have faced a few challenges. So when we try to collect the data, historical data from external source to our cloud, it was very slow because of the large volume of data. And the other challenge is when we try to read the large volume of data from our Jupyter lab, so it was very slow. We tried with multiple options. We tried to connect through ODBC. With Dremio, we tried directly connect through S3. So we tried multiple options, but it was not enough for us. And we need to train 100+ model, and our expectation is train in the short time period. And we also running daily inference with a 100+ model, and it will fire hundreds of query simultaneously. And our system should capable of handle all those queries with minimum infrastructure. And we are running with complex processing, and we also need a multi-layer lineage to handle the complexity. So I will hand over the space to my colleague Raja. He will walk through how we address all these challenges.
Okay. Thank you, Nata. Thank you for giving an overview of the project. And moving to the next one. So basically, Nata is heading our data science team, and when they are working on this project, they run into these challenges, and we have to make sure it is efficient, cost-effective, and we are able to address it so that we are able to deliver this inference and model trainings on time. And this is our data platform architecture with data lakehouse. You may have a deja vu. Thomas just presented it in the keynote. But to start with, we collect data from various data sources on the left side, and there is this data orchestration layer. We use Spark, Python, and I have put in Dremio also. Maybe I'll explain that part later when I go through future slides. And for the data storage, our data storage is in S3. So we are mainly AWS shop. So all of our products are deployed in AWS. So we use S3 with Delta Lake format too. And Dremio is the access layer and the Lakehouse engine, and even as a metadata serving layer for us. And all the users, like on the right side, if you look at it, like any users can go to Dremio. It's like one interface where people can go and look at all this data and then do ad hoc queries, analyze the things like product analyst or product managers or business analyst, right? And even data science team. They don't have to keep hunting on where is my data, which data source has it. They don't have to go and keep looking for it. Rather, it's all available in one place. So Dremio is the one interface through which all of these users come and interact. And for the data science use case, most of our data science team uses Jupyter Lab, and they connect through Dremio. And also for our model training and inference, they also go through Dremio right now for all this daily inference jobs and like monthly model training. On the right, we also have this Power BI. Power BI, we have daily reports that are on Power BI. That also goes through ODBC through Dremio to get this data. And this is, again, another view of the platform architecture from the Dremio perspective. So how we have set up in Dremio and how it is being used by different teams. So here there are these two teams. One is Shell Energy team, who is actually an energy provider, and we are Power Digital Core team, actually doing the forecast. We are helping the team by providing these forecast results to them. And when this project started, we are totally in a separate domain. AWS, they have their separate AWS account. We have our separate AWS account, and they have this data coming from different sources. On the left bottom of Shell Energy stuff, if you see, they have this data stored in S3. They have multiple SQL servers, RDBMS servers, and also MongoDB. And all this data, they have put it in Dremio, and then they use all this data here. And they can share this data also with us. So in some cases, we directly get this data through them. If you have used Dremio, you know, Dremio provides data sets, virtual data sets. So they create virtual data sets and share it with us, and we use that. And from our team, so let's take a look at the usage data. Shell Energy team, they have some internal usage data, but we also go to external vendors to get usage data. We get this data, and then we use it. And similarly, after we do the forecast results, we share these results back to Shell Energy team. We store the forecast result in our S3, and then it is shared back to Shell Energy. So there is a clean isolation between the environment. We store our data in our S3, they have it in theirs, and then we can share across using Dremio. Okay, and moving to the next part. Okay, our Dremio is again deployed on AWS. We are not yet in Dremio Cloud. Maybe we'll move to cloud in future, but right now it's all deployed in AWS. So they are using both teams are using the same Dremio environment. But still, the computations are totally different. So they have their separate Dremio Elastic engines. We have our own Dremio Elastic engines. So the jobs run by them and by us, they don't interfere with each other, or they don't impact each other's. So it's a clean isolation, and we don't have challenges with that. And on the top, if you look at it, so it's being used by various users. And we have really fine-grained access control. So we have access control set up at space level, folder level, and sometimes we don't do it at data set level frequently, but some cases we do that too. And the access control is set up so that Shell Energy team users will have only access to their data, and they cannot come and see PDC data unless it is shared with them. So similarly, same for the PDC team too. our users can only see the data that is accessible by us. And one more thing I wanted to point out here, like, so we get weather data. So we have like a large historical weather data that we store. And tomorrow in future, if there is a new energy portfolio company that, let's say, wants to come and use the weather data, we can easily share it. We don't have to get the data again or copy it or move it to them. Like we can simply share it through Dremio for them. And this is a typical process flow, which is very common. Like, so we have the data ingestion layer, data transformation, and we do data pre-processing for the machine learning use cases, and we do model training and inference. I'll talk about it in more detail in the next slides. Yeah. So I want to expand more on the data ingestion layer that I was talking, data ingestion that I was talking about. So to start with, as Nada pointed out, like one of the challenges, like getting the data from like various different sources, data sources, right? So initially when data science team was doing this job, like they were trying to put all this data in S3, like in CSV format, JSON format, different formats, try to load it in JupyterLab notebook and use it, which is like cumbersome, painful, time-taking. It slows down everything. So now we made sure like we had all these things retrieved and stored properly in S3 as Parquet. And for this, like we have different type of ingestion jobs. We use Spark and Python. They are all orchestrated in Airflow. Our Airflow is deployed on AWS Kubernetes cluster, EKS cluster, and our Spark runs on Kubernetes as well. Like we use Spark on Kubernetes. So all of these jobs are containerized and they run daily. As of now, we have all these use cases running daily. And we use Spark for like different couple of use cases here. One, historical data. So our historical data is large. In some cases, we go back up to we go for 5 years of historical data. And in some other use cases, we go up to 30 years of historical data. To get this large amount of historical data and process it, Spark was the app candidate. So whereas we were able to do a distributed processing of this and then store it, and also to partition them effectively and store it in S3. So after doing this, like this really helped the data science team. Earlier, they had challenges loading this historical data. So that was one of the things that we helped them with. And it's not only about loading. After loading, even to retrieve, storing it effectively helps them to retrieve this data faster. Okay. And other thing to mention here is like even when we store, we do different types of partitioning. I'll get back into the partitioning little later, but some partitioning we do at when we load the data itself, like simple, straightforward partitioning, like doing it on the load dates, things like that. But complicated partitioning, we leverage Dremio also to take care of that. And in the bottom left, if you take a look at it, we use the cell energies data. So cell energy team, they have their own ETL jobs, and also they have this RDBMS servers that are put in Dremio, and then they do provide their data. So, and for us, we don't really go and hit their data source or copy the data, like which is really replication of data. We don't want to do it. We directly observe the data that they provide through Dremio. And that's why I put Dremio in the ingestion layer, though it's not really ingestion, but it at least helps in avoiding this additional ETL jobs that we were that has to be done. So the next part of the thing is data transformation. Again, I'm not going to talk about the typical ETL transformations here. What I'm focusing on is mainly the transformations that we do in Dremio. Again, as I told, we use like these transformations. Like so, when there are different RDBMS tables, Cell Energy team, they join this. They do some like basic cleansing of the data. They change the format, and in some cases they do some joins, and all this data is available for us. And in some cases, there are really complex joins. Like we do like custom, for example, like so. Even to get a customer data and contract data, that cell energy team has to go to 3 or 4 data sources, like get this data, join them, and then make sure which is the proper data, and then they provide us the end data to us. So we really don't need to worry about that stuff, because they are the domain experts. They know which is the right contract data. Suppose like the contract data may be coming in from different places, but we need to make sure we are using the exact right contract data that we need to use. And even after we get that data from cell energy, we have our own usage data, weather data, and we do all these complex joins, right? So it goes like multiple levels, and it's really helpful for us to see it in Dremio and do it in do these joins, because most of our data set is SQL, and it's sometimes it's very easy for even people like product analyst or product manager who knows these things to go directly to Dremio and write these joins and give it to us. Okay. And other thing that we do is data standardization. Like as I told, like we get vendor data, usage data from internally from Shell Energy and from external vendors. So when we join this data, we have to make sure this data is same across. Like in terms like column names could be different from when we get from different vendors. So it's simple things like changing the column names, making sure the metrics that we get is in the same standard, right? So we don't want kilowatts in one place and watts in other place. So just standardizing, those kind of simple standardization we sometimes we do in Dremio too. Okay. And all this logic and then the changes that needs to be done lies with the respective team. If cell energy team does it, like they take ownership of the data. Similarly for ours. And also, because of all this too many data sources and too much layering, we have easily lineage. Typical lineage goes up to easily more than 5 levels. And this is one sample lineage screenshot. Sorry, we have to blur out the table names and stuff, because I want to keep it real. So it's from our existing environment, production environment. So the middle is the actual one of the virtual data set. And if you take a look at it, it has like five parents. And similarly, on the right, if you take a look at it, there are 4 children. And in the top children, if you look at it, it has 20 further children. And maybe if we drill down, it will go down another 2 levels or 3 levels. So easily it goes to multiple levels. And where it really helps us is to really identify, hey, this data is there, what happened, right? So we have this data. Now, say something doesn't look right with the data. So who are the parents, right? Or who is the actual source of this data, right? So we can drill down and keep going to track it till whatever level we want. So it really helps us to track this lineage and make sure we can have the right data for the forecasting. So again, the next part, like, so till now, what I have spoken is the regular data engineering stuff, where we load data from different sources, transform it, and save the curated data. And then this particular data pre-processing step, it is for the data science use case. So again, this is another thing where Nata's team, like, so they were writing some of this pre-processing as part of the data science jobs for the training and inference. And we thought, hey, this is taking more time in doing this. So how can we reduce the time? So then what we did, like we moved all this pre-processing logic also to as Airflow pipelines. So we have it as Python jobs and again Spark jobs, depending on the use case. So we do all this pre-processing and standard pre-processing, like removing outliers, like if there is null, say setting it up, data cleansing, kind of typical data science cleansing, whatever has to be done, we do it here. And we store this data again in S3, and they can be queried as feature set tables. And the model training and inference jobs mainly hit the data pre-processing layer. So right now, we don't have a separate feature store as such, but we are using Dremio itself like a feature store here. So moving to the next step, we have this data all done, like curated, now pre-processed, ready for data science. Then how are we going to enable it for model training and inference? So for model training, we run this model training like once a month, again, like during development times, like maybe too frequently, maybe once a week, or if performance is not good, we want to create a new model, again, retrain it. So we do it depending on the need. And when we do this training, because training typically queries like large set of data, then we want to make sure it doesn't impact other users. So one thing we went with is like we had separate Dremio Elastic Engine to cater to this need. So we wanted to make sure it does not impact other Dremio user or other users who are using at that time. And data partitioning. So this I referenced earlier. This was one of the challenges that data scientists were facing. So when there is like huge set of data, when they try to load this entire data set into Python notebook or anything, it can be challenging, and it's not efficient. So what we did is we partitioned the data. So there are two types of partition. We did one when we loaded, we did time-based partitioning. And for training use cases, we had to sit down with data science team, understand what type of queries they do, right? So we apply additional partitioning using reflections too. So Dremio has this reflections, which is similar to a materialized view in if you talk in database terminology, but we use reflections so that this can be retrieved faster. For example, like so they query this data as if they use cluster always to query the data, then we make sure it is partitioned on a cluster so that it only queries that set of data. And we also use the sorting feature of Dremio, where if there are high cardinality columns, we partition them, like account numbers. It's really high cardinality, we cannot partition them, but we still sort them. That also adds a lot to the performance. So when this training happens, so they are able to retrieve this subset of data that is needed for the training, and much faster and efficiently. And typical query can read this data. Like right now, it takes a couple of minutes to read the data that is needed. But when we initially started, we used ODBC to read this data. And when we used ODBC, like it used to time out after like 10 minutes or something, like even to read few million records. But now, like we used Aeroflight, and we are able to read this data like billions of records in like in around 5 minutes or so. So around like again, it depends on the data set size, but I'm just giving a general idea here. And Aeroflight, as you know, like it's used for bulk data transformation because it doesn't need serialization, deserialization, uses network properly. I mean, network efficiency with gRPC and HTTP. So it really had helped us. Like so, and right now almost all our data science use cases we use Aeroflight for this. And this comes to the last part. Here we run like this inference jobs every day. It's a daily inference jobs. Maybe in future we'll be moving up to hourly inference jobs. And even for inference, also we set up a separate on-demand inference engine. So early morning when it runs, it will kick off this engine and it will run. And for this, we have to make sure that it is tuned efficiently. So there is a separate queue, separate engine, separate user for this, and it is tuned properly. Because when the inference runs, there will be 100 inference jobs running parallelly, and hundreds of queries or thousands of queries can be triggered, can run. So we have to make sure the queuing is proper, and also to make sure it does not cause memory issues and other things. We were able, so it was a little bit of an art to fine tune this engine, but we were able to do that. And right now, our inference jobs run without any failure. And typically, most of these queries run in few seconds, actually. The next screen, I have a sample screenshot of our inference jobs. This is from our actual inference job daily. And if you look at it, like most of these queries on the duration column, if you look at it, they all run in less than a second. And maybe if it goes above it, maybe it takes like 5 to 10 seconds max, and which is really efficient for inference. Like so, we have tuned it for concurrency here, and this is how we were able to help our data science team for this load forecasting project. Thank you, everyone, and we will open the stage for question now. Yeah, sure.
Hi. So can you move to the previous slides a little bit earlier where you separate the different team to control access? Yeah.
This one? Yeah.
So first question is that, are you using Dremio Cloud or your host?
Yeah, so actually we are not using Dremio Cloud. We are using Dremio AWS engine. So we have it deployed on our AWS account, but our plan is to move to Dremio Cloud in future. And right now one of the things is with the existing edition, like we don't have like dynamic scaling of the engine. So we have on-demand engines which will come up. So let's say I have 4 nodes or 8 nodes. It will come up, all the 8 nodes has to be up always. So it cannot scale dynamically. We don't have that. In future, if we go to cloud, then we can easily scale up and down as needed.
Okay.
Yeah.
So when I see the 3 verticals, so those space, are we saying the different Dremio cluster or is it virtual space?
No, it is one. We are using only one Dremio environment.
Okay.
But spaces can be different. So here, just for simplicity, I put it as one space. Say for cell energy, they can have multiple spaces, right? So in some cases, they have, let's say, their sales team could be one, and their risk management team can be a different space, things like that. And kind of like in the same environment, these spaces are separate, and different set of users can access that depending on the need. And we have, in some cases, we have made sure the engines for the kind of we tie up, like so a simple use case is for a cell energy, like any queries run by cell energy users, right? So it will always go to the cell energy engine. So I just try to put everything in one place, like so separate Dremio engine. The coordinator will be the same, but Dremio engines will be separate for each of them.
I see.
Yeah.
So when you define the data sources, we are also separated by different concern.
Correct. So let's say cell energy team has access to 3 or 4 SQL servers that they use and a MongoDB. We don't have any of those credentials. We don't even know what it's needed. What we need is what is the data we need to use. So they make sure they add those data sources, they create the VDSs or whatever changes they have to do, right? Cleansing they have to do, the joins they have to do, and they give the final virtual data set to us. So for our team, we just make sure, okay, we use this VDS.
So given you have one controller for entire cluster for serving for 3 potential different teams, is that all the interactively query goes through the same controller? Do you experience any, the bottleneck?
Yeah, that can be a bottleneck. So the only option we have is vertically scaling now. So maybe, yeah, we did scale vertically once, right? So, but hopefully we may be moving to cloud soon,
So I was saying that moving to cloud, so that won't be the issue.
Yeah, so when we move to cloud, like Dremio provides a control plane, so we don't have to worry about the coordinator. And other benefit we'll have is like we'll have different projects. So cell energy can be a separate project, and they can own that completely. And PDC can be a separate project in Dremio. We'll own separately. The environment itself will be separate when we move. Again, it's too early for us to talk. We are yet to do POC on Dremio Cloud to move that. So.
The other question I have is that how do you manage users?
Users, we have it integrated with Active Directory. So we have Active Directory groups tied up to the spaces. So and let's say for cell energy, right? So I don't have to manage the users for that. So what we do is like the Dremio admin, what they do, like go associate an AD group with let's say for a particular space, right? Then whoever is the owner of the AD group, they can add users who can use that. And for fine grain, like we try to set different type of users, right? So we have like only read users, which means they're just only going to query Dremio, and then like read write users, they're all set up as separate groups. Read write means they can create VDS and stuff. And there is another set of users we have like admin users who can actually manage the reflections and other things too. So we want to be very careful about who enables the reflection and if they understand how these reflections are working in Dremio. So only power users like kind of like
see. Thank you.
Yeah, thank you.